In 11.1, we are doing inference about two population proportions. Our objectives include test hypotheses about two population proportions from independent samples, construct and interpret confidence intervals for the difference between two population proportions. In the book, they'll talk about independent versus dependent sampling again here. I'll talk about it in the next section. You're welcome to read the book now, but we only do independent samples for proportions. We'll do dependent and independent for means, so we'll touch on that in the next section. So we start with testing hypotheses about two population proportions from independent samples. And a note, we can proceed with our 5-step process for hypothesis testing, provided that the samples are independently obtained using simple random sampling or through a completely randomized experiment with 2 levels of treatment. We have that n sub 1 times p hat sub 1 times 1 minus p hat sub 1 is greater than or equal to 10, and n sub 2 times p hat sub 2 times 1 minus p hat sub 2 is greater than or equal to 10. And then our independence for the binomial, that n sub 1 is less than or equal to 5%, 0.05 times the population for n sub 1. And little n sub 2, our sample size for the second group, is less than or equal to 5% of its population size. And these are the same computations we've talked about before, where we can think like 20 times our sample size has to be less than or equal to population size. All right, and p hat sub 1 is equal to x sub 1 over n sub 1, p hat sub 2 is equal to x sub 2 over n sub 2. Still, our sample proportion is equal to our number of successes over our total sample size. All right, we just have 2 groups now instead of 1. So assuming those are met, we can do our 5-step process for hypothesis testing. Step 1, to determine our null and alternative hypotheses. Recall there are 3 different possibilities. We can do two-tailed, left-tailed, or right-tailed. I think this chapter is a little bit easier to set up because our null hypothesis is always going to be equality with 0, or that our 2 values are the same, so p1 equals p2, or we have p sub 1 minus p sub 2 equals 0, so we can keep that going all the way through. I'll use, I guess the one with 0, just so we get used to it for our confidence intervals as well. So our null hypothesis, we're always looking at p sub 1 minus p sub 2 equals 0, but if that difference is 0, it's the same as saying that they are equal to each other. For our two-tailed then, our alternative would be that p sub 1 minus p sub 2 is not 0. Our left tail would say that p sub 1 minus p sub 2 is less than 0, right? p1 is smaller, so we get less than 0. And then our h sub 1 alternative for right tail, p sub 1 is greater than p sub 2. Whoops, is the same as saying p sub 1 minus p sub 2 is greater than 0 now. All right, note here, p sub 1 is the population proportion for population 1, and p sub 2 is the population proportion for population 2. So all the 1s go with group 1, all the 2s go with group 2. Step 2, determine the level of significance. That's our alpha, depending on the severity of making a type 1 error. Step 3, verify the normality requirements and compute the test statistic. It'll be a z-score here. Again, we'll use technology, but the calculation is there. So we have our p hat sub 1 minus p hat sub 2. And really here, that's our sample value, if you're thinking of our normal z-score, minus p sub 1 minus p sub 2. But since we are assuming that p sub 1 and minus p sub 2 is 0, we're kind of subbing that in for the formula every time. So this is just 0, which is why it won't be written. All right, and then in the denominator, we've still got that standard error that we're dividing by. We're using p hat, this pooled sample proportion, where we put all the successes together over all of the samples. So x sub 1 plus x sub 2 over n sub 1 plus n sub 2. Again, you shouldn't have to do that ever. Step 4, we're computing the p-value. We'll get it when we run our test. In StatCrunch, if you were working by hand for the most part, you'd compute that z-score and then toss it in your normal calculator like we did through, chapter 7 and 8. All right, and then step 5, we're going to state our conclusion. If p is less than alpha, we say our results are statistically significant and reject the null hypothesis, so all those positives go together. And our other option B is all of our negatives going together. If p is not less than alpha, we say our results are not statistically significant and do not reject the null hypothesis. All right, so let's run through a couple. In randomized, double-blind clinical trials of Prevnar, a pneumococcal vaccine, infants were randomly divided into 2 groups. Subjects in group 1 received Prevnar, while subjects in group 2 received a control vaccine. After the second dose, 137 of 452 subjects in the experimental group, group 1, experienced drowsiness as a side effect. After the second dose, 31 of 99 subjects in the controlled group, group 2, experienced drowsiness as a side effect. Does the evidence suggest that a lower proportion of subjects in group 1 experience drowsiness as a side effect than in group 2 at the alpha equals 0.05 level of significance? So our alternative is a less than there, but we can start with our null. We've got that p sub 1 minus p sub 2 equals 0, or p sub 1 equals p sub 2. For our alternative, if we stick with group 1 being the Prevnar, right, we're thinking that p sub 1 minus p sub 2 is less than 0, or p sub 1 is less than p sub 2, right? So they have a lower proportion in group 1. Our alpha was given to us as a 0.05. And here we can do those quick normality checks as well. So the n sub 1 times p hat sub 1 times 1 minus p hat sub 1. I can write this one out. We got our 452 was our sample size. 137 out of 452 for our p hat. And 1 minus that gives us a 315 out of 452. And this comes out to about 95.5, which is greater than or equal to 10. For the second one, I'll just write the numbers here. We had 99 times 31 over 99 times 68 over 99. And that one came out to about 21.3. So greater than or equal to 10 there still. And for the, really the independence, the population, we've got 452 is our biggest amount of subjects, so about 500. If we multiply that by 20, we'd get 10,000. There's definitely more than 10,000 infants, so we are good to go. So we're going to run our test. We're under stat, proportion stats, 2 samples. Generally, we'll do a summary. If you do get one with just a list of values, remember you can use tables here and frequency and group them up like we did back in chapter 2. But we're going to proportion stats, 2 samples, and with summary here. For group 1, we had 137 successes out of 452 in the sample. For 2, we had 31 successes out of 99 in our sample. And we were testing for a less than here in group 1. You can always do that p-value plot still if you want to see it. We've got our test results on the first page of the output here. We can see almost our, we can see our z stat there. So here we have our z naught would be a negative 0.2. Right, if we round up, that 6 would push the 9 up, makes us a 0.20 generally. And then our p-value for step 4 would be a 0.4221. All right, which is not less than 0.05, our alpha. So with p not less than alpha, we do not reject the null. We do not have sufficient evidence that a lower proportion of subjects in group 1 experienced drowsiness. Maybe you can fit in as a side effect or something. But that's what we're looking at. That's our conclusion. And again, we've got that plot here. We can see that z-score just a little bit less than 0, so a pretty high probability of being at that score or lower. Again, right? The result we got or more extreme. So we can move on to constructing and interpreting confidence intervals for the difference between 2 population proportions. There was an option to do this with 1 sample, but there weren't too many options in the homework, so I kind of saved it for here, but it would work the same way. Here we're looking for our difference to be 0, so essentially what all this says is that if 0 is in the interval, it's a possible value for the difference, so we wouldn't be able to reject that 0 is the true value. If 0 is not in there, we've got pretty good evidence that there is a difference. In the one sample testing, if you ever look it up or see it somewhere else, we're just looking for is the assumed value for the population parameter in our interval. But for this one, recall the level of confidence 1 minus alpha times 100% in a confidence interval represents the percentage of intervals that will contain the unknown parameter if repeated samples are obtained. So we are going to do two-tailed hypothesis testing using confidence intervals. And the confidence interval estimate of p sub 1 minus p sub 2 is given by p hat sub 1 minus p hat sub 2. We take that quantity and subtract the error for the lower bound, and then we take that p hat sub 1 minus p hat sub 2 quantity and add the error to get the upper bound. So we expect p sub 1 minus p sub 2, that difference between the population proportions, to fall between those two values, where E is given by our z-score times that standard error again, so z sub alpha over 2 times our square root. For this one, we have p hat sub 1 times quantity 1 minus p hat sub 1 over n sub 1, plus p hat sub 2 times our quantity 1 minus p hat sub 2 over n sub 2. Note here, when testing our null hypothesis, p sub 1 minus p sub 2 equals 0, versus our alternative hypothesis, p sub 1 minus p sub 2 not equals 0, if a 1 minus alpha times 100% confidence interval contains 0, we do not reject the statement in the null hypothesis. However, if the confidence interval does not contain 0, conclude that p sub 1 minus p sub 2 is not 0 at the level of significance alpha. So again, this one a little bit easier. We are just looking for whether or not 0 is in the interval. Is 0 a possible value for that difference? Note, we can proceed with the confidence interval provided that same requirements as before for the hypothesis test. Samples are independently obtained using simple random sampling or through a completely randomized experiment with 2 levels of treatment. N sub 1 times p hat sub 1 times 1 minus p hat sub 1, and our quantity n sub 2 times p hat sub 2 times 1 minus p hat sub 2 are both greater than or equal to 10. And n sub 1 and n sub 2 are less than 5% of their respective populations. So for number 2, we have the Harris poll conducted a survey in which they asked, how many tattoos do you currently have on your body? Of the 1,205 males surveyed, 181 responded that they had at least one tattoo. Of the 1,097 females surveyed, 143 responded that they had at least one tattoo. We want to construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly from the proportion of females that have at least one tattoo, and then interpret the interval. So your book won't have you do a hypothesis test for all of these. Sometimes it'll just ask for the interpretation, but let's throw everything in here just so we see it all once. P sub 1 minus p sub 2 equals 0 is our null. Our alternative, we were just looking for a difference, so p sub 1 minus p sub 2 not equal to 0. Alpha here, you don't really have to think of this. We're looking more for the confidence level, but alpha is 0.05. That's what leads to our confidence level. Right, 1 minus alpha gives us a 0.95. And then times 100% gives us a 95% confidence. All right, and then we can do our checks to make sure we've got enough successes and enough failures for each. So we have our n sub 1, the 1205, times we had 181 out of 1205, and that gave us a 1024 out of 1205. And when I multiplied all those together, I got about a 153.8, right, greater than or equal to 10. And for the second set, we had 1,097 times 143 over 1,097 times 954 over 1,097 gave us approximately 124.4, right, greater than or equal to 10. And then again, we've got 1,205 males. If we multiply that by 20, we get a 22,000, 24,000 something. So definitely more than 25,000 males in the population, and more than 21,000 females. So we're good to go. All right, so for our computation, we're in the same menu. Stat, proportion stats, 2 samples with summary. We got to put in our 181 out of the 1,205 males and 143 out of the 1,097 females. We're going to choose confidence interval this time and do that 0.95 for our confidence level. We can do our computation, and we get our lower limit and our upper limit. So we're going to put that in our step 3 here. So we got a minus 0.0085 4 just looked clean, and then we got a 0.0482. It'll tell you in the problem to go to 2 or 3 decimals generally for it, but all we want to see here is that 0 is in the interval, right? We go from a negative value to a positive value. So step 5, we've got 2 things. We can do the interpretation. Always starts with we are blank percent, in this case 95% confident. The true difference in the population proportions is between our lower limit minus 0.0085 and our upper limit 0.0482. And then if they do ask for a conclusion, which shows up in some of the questions, right, not just the interpretation, but what do we actually see? We can say because 0 is in the interval, we do not reject the null. We do not have sufficient evidence of a difference in the proportion of males and females with at least one tattoo. All right, so that's it for the section. Hopefully you're getting used to the menus. We did confidence intervals and hypothesis testing, and now we're just doing 2 samples, but the same spot for each. Just make sure you're putting in your values for your 2 samples. Conclusions work the same way, all the positives together, all the negatives together.